closed transition Wye-Delta starter allows a motor to start at a reduced voltage, then switch to full voltage once the motor reaches a certain speed. This reduces inrush current and torque during startup. The starter uses two contactors. The first connects the motor in a Y configuration, which is like having three equal resistors in series with each of the motor's phases. The second connects the motor in a delta configuration, connecting the motor's three phases directly to the power supply. In operation, the motor starts in the Y configuration. This reduces the voltage applied to the motor by a factor of the square root of 3. Because of this, the inrush current and torque are also reduced. After a short delay, typically around 10 seconds, the delta contactor closes, connecting the motor directly to the power supply and applying full voltage. Considering the issue with the 150 kilowatt, 440 volts, 249 volt load amps compressor motor, there are several possible causes for the blown fuses. Firstly, a contactor malfunction could be the problem. The delta contactor might not be closing properly. This could result in the motor being connected to the power supply in a Wye-Delta configuration, an unintended state. This causes a significant increase in current because the motor operates with reduced voltage but also increased impedance. Secondly, a starter wiring error could be the issue. The starter may be wired incorrectly so that the delta contactor closes before the Y contactor opens. This also results in the motor being connected to the power supply in that unintended Wye-Delta configuration, creating the same current surge problem. Thirdly, an overloaded motor could be the cause. The motor might be drawing more current than the starter is designed for, causing the fuses to blow. Check the motor's load and compare it to its rated capacity. Fourthly, a mechanical fault in the motor could be to blame. A short circuit or a seized bearing could cause the motor to draw excessive current, blowing the fuses. Thoroughly inspect the motor for any signs of mechanical problems. Based on the current readings provided, some clues can be identified. Starting in the Y configuration with 530 amps suggests a healthy initial current draw, roughly around 2 times the motor's full load amps, which aligns with the typical reduced voltage start. The drop to 130 amps when the delta contactor closes suggests the transition occurred, but the subsequent spike to 1270 amps is very concerning. This high current surge before the fuses blew indicates a severe problem during or immediately after the transition to the delta configuration. Given the symptoms, focus on the following troubleshooting steps. Firstly, carefully inspect the starter wiring. Verify that the Y and delta contactors are wired correctly according to the manufacturer's specifications. Ensure there are no loose connections, damaged wires, or incorrect terminations. Secondly, check the contactor sequence timing. Use a multimeter or oscilloscope to verify that the Y contactor opens fully before or at the exact same time as the delta contactor closes. Any overlap in their operation can cause the described current surge. Thirdly, examine the contactors themselves. Inspect the contactors for damaged or worn contacts. Look for signs of overheating or mechanical failure. A malfunctioning contactor can cause improper switching and current spikes. Fourthly, check the motor load. Ensure that the compressor is not overloaded. Verify that the compressor is operating freely and that there are no mechanical issues causing it to draw excessive current. Fifthly, perform a motor insulation test. Use a megometer to test the motor windings for insulation breakdown. A low insulation resistance reading indicates a potential short circuit within the motor. Sixthly, verify the utility voltage. Confirm that the utility voltage is within the acceptable range for the motor. Low voltage can cause the motor to draw more current. Seventhly, check the starter's overload protection. Verify that the starter's overload relays are properly sized for the motor's full load amps. A correctly sized overload relays may not protect the motor from excessive current draw. Eighthly, consider harmonic distortion. Investigate the possibility of harmonic distortion in the power system. Harmonics can cause increased current draw and overheating in motors and transformers. Ninthly, verify the transformer bank capacity. Although a 225 kV transformer bank should be adequate for a 150 kW motor, ensure that the transformer is not overloaded and that it is properly sized for the application. 10thly, analyze the fuse type and rating. Confirm that the fuses used are the correct type and rating for the starter. Using incorrect fuses can lead to premature failure. Also, review any event logs on the starter or the motor protection relay, if available, for additional diagnostic information. Reviewing the motor nameplate information and comparing it to the system parameters can help to identify discrepancies. Additionally, closely monitoring the voltage during the transition period using a transient voltage recorder can reveal voltage sags or other abnormalities that might be contributing to the problem. If the issue persists after these steps, consider consulting with a qualified electrician or motor specialist for further assistance. Be sure to thoroughly document all observations and measurements taken during the troubleshooting process. Also, confirm that the closed transition resistors, if present, are of the correct ohmic value and are not damaged. Incorrect resistor values can also result in current surges during the transition. Be mindful of the potential hazards of working with electrical equipment. Always de-energize the equipment before performing any testing or maintenance, and follow all safety precautions. Using appropriately rated personal protective equipment is a must. Specifically regarding the closed transition Wye-Delta starter, the closed transition design aims to minimize current surges during the switch from Y to Delta. This is achieved by momentarily closing a transition contactor that keeps all three motor windings energized during the changeover. Without this, there would be a brief period where the motor is completely de-energized, which can lead to a large inrush current when the Delta contactor closes. When diagnosing issues with this type of starter, pay close attention to the timing and operation of the transition contactor. It must close before the Y contactor opens, and it must open before the Delta contactor closes. If there is any overlap or delay in these operations, it can cause significant current surges. Also, examine the transition resistors if used. These resistors are placed in series with the motor windings during the transition period to limit the current. If the resistors are damaged or have the wrong resistance value, they won't be able to effectively limit the current, leading to surges. Remember to consult the starter's manual and wiring diagrams for specific details on its operation and components. This will provide valuable information for troubleshooting and identifying potential issues. Finally, consider the ambient temperature and ventilation of the starter enclosure. Overheating can cause components to malfunction and lead to premature failure. Ensure that the enclosure is properly ventilated and that the ambient temperature is within the starter's operating range. Keep in mind that electrical systems can be complex, and it's always best to consult with qualified professionals when dealing with potentially hazardous situations. If you are not comfortable working with electrical equipment, please seek the assistance of a licensed electrician. A systematic approach to troubleshooting, combined with a thorough understanding of the system and its components, will help you identify and resolve the problem efficiently and safely. Considering the specific values you provided, let's dig into these. The motor is 150 kilowatts, 440 volts, with a full load amps of 249 amps. The transformer bank is 225 kilovolt amps. During starting, the current in the Y configuration is 530 amps. 10 seconds later, the Delta contactor is closed, and the current dropped to 130 amps. 1 second later, the load shot up to 1270 amps. The inrush current in the Y configuration at 530 amps is about 2 times the full load amps, which is typical for reduced voltage starting. The drop to 130 amps when the Delta contactor closes suggests that the motor is running at a reduced load or speed during that brief period. The spike to 1270 amps is almost 5 times the full load amps, which is an extremely high inrush. This indicates a severe transient condition. The fact that the transformer bank fuses blew after 1 second of this condition confirms that the current was significantly over the transformer's capacity. To analyze the situation further, consider the following. The transformer's rated current can be calculated using the formula kilovolt amps equals root 3 times volts times amps. So amps equals kilovolt amps divided by root 3 times volts. For a 225 kilovolt amps transformer at 440 volts, the rated current is approximately 295 amps. The transformer can likely handle short duration overloads above its rated current. However, a sustained current of 1270 amps is significantly beyond its overload capacity and would cause the fuses to blow quickly. It is vital to verify the transformer's impedance. A lower impedance transformer will allow a higher fault current to flow, which can exacerbate the issue during the transition. Also, confirm that the transformer's protection is coordinated with the motor starter's protection. This coordination can result in the transformer fuses blowing instead of the motor starter's overload relays tripping. The transition from Y to Delta should be seamless and without any significant current spikes. The fact that you are seeing such a large spike suggests a problem with the transition process. The most likely causes are related to the timing and operation of the contactors and the transition resistors if used. The starter supplier being at a loss is concerning. They should have detailed knowledge of the starter's operation and troubleshooting procedures. Consider seeking a second opinion from another motor control specialist. If possible, obtain a recording of the motor's voltage and current during the starting sequence. This data can provide valuable insights into the transient behavior of the system and help pinpoint the cause of the problem. Also, carefully inspect the motor's rotor. A damaged rotor can cause unbalanced currents and excessive heating, leading to premature failure. Compare the motor's actual performance to its expected performance based on the manufacturer's data. This can help identify any deviations that might indicate a problem. Also, consider the impact of the starting method on the motor's lifespan. Reduced voltage starting methods like Wye-Delta starting can reduce the stress on the motor windings during startup. However, they can also result in longer acceleration times, which can lead to overheating if the motor is not properly sized for the load. Verify that the motor is adequately sized for the application and that it is not being subjected to excessive starting duty. Furthermore, check the condition of the cables connecting the motor to the starter and the starter to the power source. Undersized or damaged cables can cause voltage drops and increased current draw. Confirm that the cables are properly sized for the motor's full load amps and that they are in good condition. Lastly, consider the impact of the starting sequence on the power system stability. Large motor starting can cause voltage dips in the power system, which can affect other equipment. Ensure that the power system is adequately sized to handle the motor starting load and that there are no other sensitive loads that are being affected by the voltage dips.